Before we move on to testing multiple proportions, we'll do a two proportions review. So we've talked about comparing one proportion to an assumed proportion, also called an historical or ahistorical proportion, where you take a new sample and compare it to what you assumed the proportion would be based on prior information. This is not generally or frequently done in scientific research. We usually have two samples, say a cases and a control, or a new treatment versus existing treatment, or a new intervention versus considered standard of care intervention. So we usually have two samples that we're comparing. And we've looked at Fisher's exact test, as well as the shortcut chi-square test, as well as the regular chi-square test, as well as a z-test. So the one proportion z-score that goes with the null hypothesis of p hat equaling p naught. Remember, p hat is your estimated proportion, and your p naught is your null proportion. We can calculate a z-score from this. Recall that p naught is what you use for your standard deviation because we are assuming the null hypothesis is true. For two proportions, it's not that different. Instead of directly comparing P1 and P2, we'll take the difference of P1 and P2 and compare that to 0. So this is exactly the same as your one sample z-score, where P naught is 0 and P hat now is the difference between our two proportions. See here, we have P2 minus P1 in parentheses. We could call that p hat, the difference of the two proportions, and we could compare it to 0. But instead, of course, of using a standard error associated with 0, what we'll utilize is what's called a pooled standard error, or the average standard error from our observed proportions. You can set this up as P1 minus P2 or P2 minus P1. So it depends upon the type of test you have, one-sided or two-sided, and it also depends on the direction of the difference. For two-sided tests, simply set it up to use a positive difference. For example, we wouldn't want to say that we had a negative 4 pounds of weight loss, because that would actually be 4 pounds of weight gain. So you need to adjust your thinking or your test statistics that you report to be in positive values. We have a 4-pound weight loss. For one-sided tests, it's really critical to make sure that your subtraction is the same direction as the test. But remember, you can actually set this up any way that you'd like. In JUMP or in SAS, you can order the variables so that you can get the positive difference reported as well as a positive z-score. If you're testing HA where P1 is less than P2, you can actually test either that 0 is less than that or that the proportion is less than 0. It doesn't actually matter. The statistical software will do it for you. Just make sure to remember that the difference you get will either be reported as positive or negative, and you need to make sure that you understand which p-value you are utilizing. So take advantage of the output and JUMP that gives the alternative hypotheses in words and make sure that you understand which direction you are testing. If you are doing a one-sided test, remember that it's half of the p-value of the two-sided test. So if you're in a situation where you have a two-sided p-value and you'd be interested in knowing what the one-sided result would have been, simply divide that p-value by 2. Use caution when setting up one-sided tests. If I have a P1 and a P2, and I observe P1 to be greater than P2, so let's say I observe P1 has a success rate of 10%, and P2 has a success rate of 5%, make sure you know which way you've calculated it. So if I do 10 minus 5, that should be a positive difference. If I see a negative difference, that means I've set it up as the 5 minus 10. And remember, if I've observed P1 greater than P2, so what my data says, that my 10% I've observed is higher than 5%, I cannot reject the test of 10% being less than 5%. So make sure you understand the direction that you are looking and the differences that you expect to see. You will never statistically show that one proportion is larger than another if you observe it to be smaller than. Conversely, you'll never show that one proportion is smaller than another proportion if you've observed it to be greater than. Recall we have 3 tests of hypotheses for 2 proportions: equal to, not equal to, less than or equal to, greater than or equal to, less than. Remember, the equal sign is always on the set of the null side. If you have a P1 and a P2, you still only have 3 sets of hypotheses. This time we're just comparing it to 0. And again, just a reminder, if you observe P1 minus P2 is less than 0, a negative number, you will never reject testing it to be greater than 0, or if the converse is what you're looking at. So if you observe something to be larger than something else, you will never show the alternative of it being smaller than. If you want to show P1 is larger than P2 and what you actually observe is P1 less than P2, you will have a large p-value. You will never show that. If you want to show that P1 is smaller than P2 and what you observe is P1 larger than P2, you will never show that P1 is less than P2. So keep that in mind. It's very important when planning studies. You need to know what you expect to see. If you have no idea which group will be larger, plan a 2-sided test. So do the equal to, not equal to test. If all you care about is P1 being larger than P2, so the proportion of success in my group 1 is higher than my proportion of success in group 2, then plan a 1-sided test. If all you care about is showing that something is less than, then plan the 1-sided test in that direction. If you don't know, if I have no expectation of which group will be larger than the other group, then plan a 2-sided test where my alternative is not equal to. So I'll run through a quick example here from 2008. This was the proposed financial bailout, and it failed to pass in the United States House of Representatives. The final vote was 228 no and 205 yes. There's a number of things you can collect from this data, and you can find it at the New York Times. If they needed a majority of 50% to pass the bill, we could ask, is the proportion that voted yes significantly less than 50%? There were 433 representatives. Exactly 50% would be 216.5 yes votes. We wouldn't actually have that. So we'll look at 217 for a majority. So is 205 yes votes really less than a majority vote? We can look at our test statistic here. We can get a z-value here of minus 1.15. We can find the p-value, either the normal approximation or the exact p-value, and we can find the Wald statistic or the CI score confidence bounds. Both of these, either of these, will tell you that our p-value is greater than 0.05. We're going to fail to reject our null hypothesis. And our decision here would be that the proportion of yes votes is actually not statistically significantly less than a majority vote, if a majority vote is 50.12% yes. So how would we say this? Did the bill statistically pass then, if it's not different than 50%, even though the bill failed? Of course, we know this is not the way that voting works. It's a hard majority based on the counts. But you could see from this example, while an observed majority won, the statistical comparison resulted in equivocation. We failed to reject a difference from 50%. Are there issues with this type of test? Think about independence and representativeness. And again, remember, you have to look at your sample size issues. What about looking at how Democrats voted versus Republicans? You could consider the following table. This is a breakdown on party line with no votes and yes votes out of the 433. Our question is the proportion no the same across parties? We could also ask if the proportion yes was the same across parties. Answering either one, remember, answers both. We'll either ask about the proportion no or the proportion yes, but we're not asking if the yes equals the no, and we're not asking if they equal 50%. Is our observed proportion of Democrats that voted yes equal to our observed proportion of Republicans that voted yes versus our alternative where they are not equal to? So we'll use the yes proportion. Step 1, describe our data. Got 59.6% of Democrats voted yes, 32.8% of Republicans voted yes. For steps 2 and 3, you could look at independents. That's questionable, as we know these things tend to be voted in blocks, but let's assume independents, that each person voted their own way. Representativeness, maybe. That's a larger discussion. In sample size, well, you could use JUMP to get the expected cell counts here. In step 3 would be where we give our hypotheses. Steps 4, 5, and 6, since we have a chi-square or a z, we know what 5 and 6 would be, and we know that we'll reject h0 for a small p-value, and let's assume our alpha is 0.05 here. We could use either the z-test or the chi-square, and we could use the chi-square or the quick chi-square with our counts. We get a 5.553 for a z and a chi-square of 30.836. Try to set up this data in JUMP and see if you can find these same statistics. Just note that the square root of a chi-square of 30.836 is actually 5.553, which is the same as the z-score. In the 2x2 situation, the chi-square will give you the same results as a z-score. And in fact, moving forward in 2x2 situations, you should report a chi-square test. Since this is a two-sided test, we can use the p-value straight from JUMP. You would use fit y by x in this case, with the party line as the x and the outcome vote as the y. Step 8, we'd get our p-value of less than 0.0001 or reject h0. We would need to put that into words because remember, the p-value is not our conclusion. The p-value simply helps us decide between the null and alternative. Step 9 would be there is sufficient evidence to conclude that the proportion of Republicans that voted yes is statistically significantly different from the proportion of Democrats that voted yes. Step 10, we'd write everything up. Give the background. The U.S. House of Representatives voted on this Emergency Economic Stabilization Act in 2008. Here's the actual date that it was voted on. Of those 433 members, we gave the overall yes number. You could give the proportion there as well. And a statistically significantly different proportion of Democrats voted yes compared to Republicans, and then give the two proportions and the p-value. You could then also calculate the confidence interval for the difference of the two. You could either use the z-score confidence interval or the walled or the exact confidence intervals. Here we'll just do a quick calculation by hand, and you can get the confidence bound here, and then you'd want to include that interpretation. You could simply give the confidence bound, or you could go further and say we're 95% confident that 17.7% to 35.8% covers the true difference between the proportion of Democrats and Republicans that voted yes to this bill. Our 95% confidence interval did not include 0. That again further supports our conclusion of the alternative hypothesis that we do have a difference in proportions. Remember, if you find a significant difference in your proportion, you should report the confidence interval. That is what the inference back to the broader population is. So I've estimated the difference to be this plus or minus this. So if we did it again, we would expect to see a difference between the lower bound and the upper bound. Somewhere in there, we'd be 95% confident that redoing this sample or this experiment would give us a proportion difference in that bound. So we've applied the 10 steps to comparing a single observed proportion to a historical proportion, and then extended that to comparing two observed proportions. We've tested two observed proportions by testing the difference equal to no difference. We'll continue to apply the 10 steps when we expand it to multiple means and multiple proportions, or single means and then on to multiple means. So we'll follow the same set of 10 steps for answering any question statistically with data. Moving forward, we'll continue to utilize the software to address these issues.